Hello everyone, my name is Filip Škola and I'll be presenting our work on interaction under whole body user rotations in virtual reality. That is what happens when we decouple your virtual body orientation from your physical one. So why is this interesting? VR lets us do things that are impossible in the real world, what some call beyond real interactions. But one affordance that remains largely avoided is altering the user's virtual body orientation in pitch or roll. The reason behind this is visuo-vestibular conflict. When what you see disagrees with what your inner ear reports about gravity, the expectation is that people will get sick. The subjective vertical conflict theory specifically predicts that sickness is most likely when the perceived gravitational vertical is misaligned between the real and virtual world. But there are compelling reasons to explore this space. Think about 3D designers who need to sculpt or paint a model from underneath. Right now, they have to rotate the object rather than themselves. Or space flight simulation, where controlled sensory conflict could serve as cost-effective disorientation training. There are also use cases in laying down VR for medical contexts or accessibility, as well as architectural visualization, VR storytelling, and gaming. So we set out to actually measure what happens. We structured this study around three research questions. First are the subjective measures, comfort, spatial understanding, dizziness, and nausea, under tilted conditions equivalent to the upright baseline. We use the equivalence testing here, not just significance testing. Second, how does task performance compare? And third, how does the tilted virtual body orientation affect perception, both of the VR environment and of your own physical body? We ran a within subject study with 30 participants, 14 female, 16 male, ages 20 to 69, median 34. Most had very limited prior VR experience. Each participant experienced 12 pitch tilt conditions ranging from 15 degrees to 180 degrees upside down, plus a baseline at 0 degrees. The conditions were presented in a counterbalanced progressive order rather than fully randomized. This was a deliberate safety decision. We expected potential nausea at extreme tilts, so we started from mild and progressed to extreme. We counterbalanced the direction. Half started with forward tilts, half with backward, and the baseline was always the sixth condition to minimize novelty and training effect. Participants used standalone MetaQuest 3S headsets with bare hand tracking, running at 72 frames per second. The total VR session lasted about 22 minutes on average. We collected in VR questionnaires per condition, pre and post experiment simulator sickness questionnaire, task performance metrics, and open-ended qualitative responses. Here you can see the full set of conditions. Forward tilts positive go from 15 up to 150 degrees. Backward tilts mirror that on the negative side, and then 180 degrees is fully inverted. Importantly, participants were physically seated in a chair throughout. The rotation was applied entirely to their virtual body and the surrounding environment. Transitions between conditions were triggered by pressing a button and used a 4-second fade-out fade-in sequence to avoid sudden visual changes. The VR environment was a modernist interior, an 8 by 8 meter room with various gravitational cues like asymmetric furniture, a ceiling fixture, and frame images of upright human figures. Central to the room was a large 24-sided working wheel that served as both the task workspace and a spatial anchor. We used two tasks. The docking task required participants to pick up a cube, rotate it to align the marked face, and insert it into a matching hollow on the wheel panel. 3 trials per condition. This tested sustained hand-eye coordination, mental rotation, and precision alignment under altered egocentric pitch. We measured completion time and positional accuracy. The shooting task required aiming a laser at spheres scattered across a wide angular range and maintaining 1 second of uninterrupted contact. 7 trials per condition. This tested pointing, continuous stabilization, and visuomotor correction. Both task interactables were rotated along with the user, modeling scenarios where you would rotate your virtual posture to match the interaction demands. A 6-item in VR questionnaire was completed after each task set. Now for the results, starting with the subjective measures. The main finding, nausea was equivalent to baseline in all 12 conditions, including 180 degrees, fully inverted. The equivalence tests were significant at p less than 0.001 for every condition. The simulator sickness questionnaire nausea subscale confirmed this with a negligible mean of 3.82. Only one participant out of 30 reported a notable nausea score. Disorientation remained equivalent to baseline up to plus or minus 19 degrees. Beyond that, a plus or minus 150 degrees, we saw a mild increase of about 2 points on the 7-point Likert scale. Comfort and spatial perception were equivalent to baseline up to plus or minus 45 degrees. Beyond that, they declined slightly, but comfort ratings consistently stayed in the favorable range, between 5 and 7 on the scale, even at extreme tilts. The overall simulator sickness questionnaire total was minimal at 9.1. To put that into context, many VR studies with standard locomotion report substantially higher scores, so the sickness results were considerably better than we anticipated. For performance, the shooting task showed results that were either equivalent to or slightly better than baseline at most tilts. Forward tilts in particular showed a trend toward improved performance. No significant degradation was observed at any tilt angle. The docking task was more nuanced. We observed a speed accuracy trade-off. During forward tilts, participants were slightly more accurate but slower. During backward tilts, they were faster but less accurate. Neither the time nor accuracy differences reached statistical significance compared to baseline. So performance was affected but not systematically degraded. A few patterns are worth highlighting. First, there was no systematic worsening. Performance didn't just get worse as tilts got more extreme. Second, the direction mattered. Forward tilts were consistently better tolerated than backward tilts across tasks and subjective measures. Third, and this is an interesting observation, we noticed that small tilts, particularly plus or minus 15 degrees, sometimes produce worse performance spikes than larger tilts. We interpret this as a kind of sensory mismatch uncanny valley, where the conflict between visual and vestibular cues is subtle enough to create reference frame ambiguity. At larger tilts, the conflict is unambiguous, and the perceptual system can commit to the tilted frame and adopt more stable motor strategies. For the perceptual effects, the reported illusions of gravity pull and body orientation peaked around plus or minus 150 degrees and interestingly declined at 180 degrees. But overall, these were modest, rarely exceeding 3 out of 7 on the Likert scale. About a quarter of participants experienced vivid body tilt illusions, while many others felt very little. Sense of ownership and agency over the virtual hands remained strong throughout. The qualitative data told a consistent story. Participants reported rapid adaptation. Initial discomfort at the start of a new tilt would quickly subside. Several participants noted that the plus or minus 90-degree and 180-degree tilts, the wall-aligned orientations, actually felt more natural than angles like plus or minus 45 or 150 degrees, likely because they aligned with the visible room surfaces. People describe the experience positively. Words like immersive, convincing. One participant said it felt like I was meant to be Spider-Man, so weirdly natural. So, what does this mean for VR designers? We can distill several actionable guidelines. Tilts up to plus or minus 45 degrees can be deployed with confidence. Comfort, spatial perception, and sickness are all equivalent to baseline. Forward tilts should be preferred over backward. The plus or minus 90 and 180-degree tilts can be surprisingly well tolerated, but the plus 90-degree forward tilt can cause occasional disorientation and should be used with care. And minimal onboarding is sufficient. Users adapt quickly. Considering the limitations, the progressive design may have facilitated adaptation that reduced sickness at extreme angles. The working wheel served as a spatial anchor that likely helped orientation, and we only tested relatively static tasks. Dynamic tasks and higher order cognitive demands like spatial updating and mental rotation remain untested. To wrap up, VR interaction under arbitrary whole-body pitch rotations is feasible without significant compromise to comfort, nausea, or task performance. Users adapt rapidly, and the design space for orientation decoupled VR is wider than previously assumed. For future work, we are looking at longer exposure with dynamic and cognitively demanding tasks, removing the spatial anchor, randomizing tilt exposure, and eventually exploring user control orientation changes and non-seated conditions.